Hello dear students, welcome to Axiomaticos. This video is the part of the solution series for PhD entrance exam of mathematics recently conducted by Indian Statistical Institute, and it's a 2020 paper and we are here with this problem 9. So have a look. Let f such that c to c be an entire function that is analytic everywhere in C. Suppose this limit mod z goes to infinity fz over z is 0, then what we have to prove? We have to prove that your function f is a constant function. Alright, so now let us write quickly that what is given to us. It's given to us that f such that c to c is entire. Now the second thing that is given to us is this, that limit mod z goes to infinity fz over z approaches 0. All right, so what is the meaning of limit mod z goes to infinity fz over z? It has a simple meaning that when you will choose any epsilon greater than 0, all right, so you choose any epsilon greater than 0, you will get this, that mod z by z minus 0 is less than epsilon for sufficiently large z. Are you getting my point? Large z. So whatever epsilon you will choose, you can always find a z after which you will have this inequality to be true. Are you getting my point? So after that number you will get every z such that this inequality will be true. So this is what your question is, this is what is this limit actually means. So what we can do, we can rewrite this thing like this, is less than epsilon times of mod z. Now see, this inequality is true for every epsilon. It means that whatever epsilon you will choose, you will always get a z after which you will get this inequality. Are you getting my point? So that means when I will be choosing my epsilon to be smaller than 1, then what will be happening there? If you will choose, let us say I am choosing epsilon to be less than 1 by 2. So less than 1, sorry. So let us say epsilon is 1 by 2. That means you will get mod fz is less than mod z by 2. So mod z by 2 is less than mod z. That means that this thing is smaller than mod z for sufficiently large z. Now using this thing, I will be proving that your function fz is some constant. All right, so I will be proving that this function is equal to some constant using this. So what I will be using, I will be using Taylor expansion. I will talk about that later. So now let us see that you have this. We know that this formula holds for entire function, that fn of 0 is equal to fz by z minus z naught. I should write in place of z naught we have 0 in this case, z minus 0 to the power n plus 1 dz n factorial by 2 pi I. You know this, right? That this formula is true. You all know this from the complex case. So we have this result with us. Now what I will be doing, I will be applying mod on both sides. All right, so I should also write on which loop you are working. So you are working on a circle CR. CR is a circle of radius r at origin. This is your CR. All right, so we are integrating this thing on the circle CR. We can do this, all of these things, because your function is entire. So if I will apply my mod here, I will get this mod of n factorial by 2 pi I integration of fz by z to the power n plus 1. Now see, if I take this mod inside of the integral, you will get an inequality. All right, so if I am taking this I will be removed, so I should erase this. So if I take my mod inside, I will get this mod of fz by mod of z to the power n plus 1. All right, and here we have dz. So now from here what I can write this, that this thing is smaller than n factorial by 2 pi max of fz, or you can say supremum, you can take anything. I am just considering this to be the bound. All right, so what is this representing? This I'm just writing max, but it doesn't mean max. This represents the bound of mod fz on the circle CR. All right, you will get this. Now on the circle CR, this z mod z to the power n plus 1 will be r to the power n plus 1, because what is the equation of a circle of radius r centered at origin? This is the equation of circle centered at origin with radius r. So that is why I can replace mod z to the power n plus 1 with this. So I got finally this. Are you getting my point? dz on circle CR. What is this integration representing now? This integration is representing the parameter of the circle at origin with radius r. So what is the parameter? It's 2 pi r. So finally what I will get? I will get that fn of 0. All right, now in place of this thing, what I will be writing? I will be writing this, that mod of fz is less than this. I was trying to find some bound for this. That is why I can replace mod z with it. So I will get this. I will replace mod z, and you know that mod z on a circle CR is just r. Are you getting my point? This thing, I am replacing this with mod z, and mod z on CR is r. So you will finally get this 2 pi r. Are you getting my point or not? So this is what you are getting. So finally I will get fn of 0 is less than n factorial by 2 pi, and I think what you will get here, you will get 1 by r to the power n minus 1. All right, so if your n now, the n that you have, not all right, n, the n that you have is, suppose this n, I made a mistake or something else. Let me check whether I made a mistake or not. All right, so everything is correct. I thought that I made a mistake, but now it's not there. Everything is correct. So we got this inequality, right? Now if I am considering my n to be greater than 1, then what will happen? If you will increase your r, this thing will be going towards 0. All right, so we know that this inequality is true for a sufficiently large z. So what I will do, I will increase the radius. All right, so I will increase up to where I can increase. I can increase it infinitely many times. So I will just apply r goes to infinity. So when r is going toward infinity, this thing is going towards 0. So for sufficiently large z, what will happen is this, that fn of 0 is less than 0. Are you getting my point? For sufficiently large z, this thing is happening. Now let me erase this part, and then we will tell you what is the step after this. So see, what we have is fn of 0 is less than 0 for sufficiently large z. All right, so there will be equal to also. So this is mod, so it's a positive thing. So what we will get, fn of 0 is 0. This is what we will get, that fn of 0 is 0. All right, so from this thing, what we can say, that this derivative of f at 0 is 0 for all n greater than 1. Now let us use its power series. So since it is entire, that means you can write its power series, or you can say Taylor series also, like this. F dash of 0, then you will get z minus 0 whole square by 2 factorial, f double dash of 0, and so on. Alright. So you know that derivative after 1 is 0. So from here what you are getting? That fz is equal to f0 plus z of f dash of 0. So now let us consider f0 to be a and f dash 0 to be b. So what you will get? You will get a plus zb in that case. Now I will show that this b is 0. Okay. What I can use, I will tell you now. Let us erase this part, because this is what we will be needing. So I am writing here in this box. Alright. So we got fz like this. So now calculate this limit. Fz by z. What is fz? Fz is, finally we proved that fz is mod z, sorry, mod a plus zb, sorry. So you got this. So do you think that this limit is equal to 0? No, it cannot be, because you will get a by z plus b. So this limit will be equal to b. Are you getting my point? Because z is going toward infinity, so this thing will be 0. So you will get b here. But in the question it was given to you that this is 0. So therefore b is 0. So finally from here we can say that your function is like this. Fz is equal to a only. That means it's a constant. So now let me explain everything. Let me conclude everything what I have done. I proved initially that mod of fz is less than mod z. Alright. Then I used this thing to show that fn of 0 is 0 for all n greater than 1. Then using the Taylor expansion, I showed that fz is a. So this is what I have done. It was an easy question, but the catch of this question lies in the initial step. What was that step? That mod of fz is less than mod z for sufficiently large z. So this is what we needed, and finally we proved everything. Alright. So thank you.